Howdy, AP PreCal. It is Miss Kosh. I am finishing up the notes for 2-1 and 2-2. I broke it apart not between 2-1 and 2-2, but I broke it apart between arithmetic and geometric. So that's just the way that it made sense to me. I'm assuming that you watched my previous video. So I basically did the same exact structure for arithmetic that I'm now doing for geometric, but I'll probably go faster since we already understand the first part. Okay, successive terms in a geometric sequence have a common ratio, or, and this is language that's kind of new to me, so let me make sure I'm not lying to you, or a constant proportional change. So it doesn't have a constant rate of change, it has a constant proportional change. Okay, so they give us the sequence 2, 4, 8, 16. Notice, hopefully, that we're multiplying by 2 each time. The first term was 2, the common ratio was 2, and a sub n, well, it's just 2 to the n. So when I plug in the first term, plug in 1, that's 2 to the 1 is 2, plug in 2, 2 squared is 4, plug in 3, 2 cubed is 8. And then when I go to plot these points, basically I'm plotting the point 1, 2, and then this is the second term was not 2, 4, sorry. The third term was 8, and so forth. So here's these are the output values, and the input values are what term it is in the sequence. So let's see if I can see what I'm doing here. 1, we're at 2, 2, we're at 4, 3, we're at 8, and 4, we're at 16. 5 would be at 32, which would be even higher up here. It's not on there you go, you can see it. That dot, it's not on the graph, but you'll notice, hopefully, that this becomes an exponential curve. And once again, like the linear, we can't connect those because these have a domain of whole numbers and not a domain of real numbers. Okay, if that doesn't make sense, let me know. Okay, the general term can be written, these two were what show up in these two are the AP style. And I just really I've been using this one, so this is the one that Miss Kosh loves. So it just makes sense to me, and I can't quite walk away from it. But I'm getting better at understanding why AP does what they do. So what we can find here is that if I have we'll call it the G sub 1 is the first term, and G sub 2 is the second term, and G sub 3 is the third term, and G sub 4 is the fourth term, G sub 5. Okay, and then we can kind of keep going. What we're doing here, when we have a common ratio, I have to go from G sub 1 to G sub 2, I'm multiplying it by my common ratio. To go from here, from the second term to the third term, I'm multiplying it by that common ratio again. So let's say I want to go from the first term and get to the fifth term. I have to multiply by my common ratio 1, 2, 3, 4 times. So G sub 5 would be equal to G sub 1 times R to the fifth. I lied. Did you catch that before I just did it? R to the fourth. So sorry. We said 1, 2, 3, 4, and then I wrote a 5. I don't know. Okay. Let's say, what if I want G sub 10 and I'm starting at G sub 1? We have to multiply the common ratio 9 times. Okay. If I want the 20th term and I'm at the first term, I have to multiply by the common ratio 19 times, so that's R to the 19th power. What we're saying here is that G to the n would be equal to G to the 1 times R to the n minus 1. Or you could back it up to the term that came before. If I know the 0 term, which we don't include on the list of terms, then I would have to say I want the fifth term, I'd have to multiply it 1, 2, 3, 4, 5. And so this is the way they write it. They say, nope, they say G sub n is equal to G sub 0 times R to the n. Okay, notice those numbers are adding to this. These numbers are adding to this. These numbers are adding to that. Yeah, that's a thing. Okay, and likewise, if we have G sub n is equal to G sub k, if we start at some random term, this is R gets raised to the n minus k. Okie dokie. How does this relate to the exponential functions? The way that I was relating, you know what, I have my book right here. Okay. Yeah, that's just kind of weird. What I would do is I would relate this one, and this becomes y is equal to our initial amount, we often call A, and then our ratio, or like our growth or decay factor would be B. And so if you remember from Algebra 2, and we're going to talk about it again, but this would be like y is equal to A times B to the x, because G sub 0 is our initial amount, and this is our common ratio, or our growth factor, or our decay factor, raised to that independent variable. They write this out differently, but it just, I think I would confuse you at this point. I mean, it's fine. All right, you know what? Here's what they say in the booklet. They would say that this, oh, and I should have said f of x. They would say f of x is equal to y sub I. Oh, I just realized why they write y sub I. R to the x minus x sub I. It's the initial amount. That's why they're using an I. I should, if you watched the previous video and I was like, I don't know why they picked the I just figured it out. Initial. Ah, fantastic. Is it initial? No, it's not even the initial. I don't know why they pick an I, but there we go. Okay, let's actually jump in and do some problems and hope this makes a little more sense. The second term of a geometric sequence, we can call it any letter, but I keep using G for geometric, or I use A as a default a lot of the time. So G sub 2 would equal 250, and the fourth term, G sub 4 equals 40. Okay, and what we know is that G sub 4 would be equal to G sub 2 times R squared. So G sub 4 is 40 equals 250 times R squared. When I divide, I end up with 4 over 25 is equal to R squared. And now you might remember it's square root, plus minus. And so my R value could actually be both plus or minus 2/5. Square root of 4 is 2, square root of 25 is 5. Okay, if that's the case, let's see what happens here. Let me show you this. I can say that G sub 2 would be equal to G sub 1 times R to the first power. So if I have the second term and I want the first term, I just have to multiply it by the first. Let's try that again. The first term times R gives me the second term. There we go. So the second term was this 250, and then this is equal to a 2/5 times G sub 1. I wrote it in backwards. I apologize. So 250 needs to get divided by 2/5, and so that is 625. So watch what happens here. If I take, delete all, that's what I wanted to do. If I take 625 and I multiply this by 2/5, this is my second term, here's my third term, here's my fourth term. Okay, and I can keep going, whatever. But also notice, if I start with a negative 625, and instead of multiplying it by a positive 2/5, if I multiply this times a negative 2 over 5, we have a positive 250 for our second term. We have a negative 100 for our third term. We have a positive 40 for our fourth term. So both of these scenarios, both G sub n equals 625 times positive 2/5 to the n minus 1, and G sub n is equal to negative 625 times a negative 2/5 to the n minus 1. Both of those will generate sequences where the second term is this and the fourth term is that. Okay, so there were two answers, and so we need to find the seventh term of both of those. So if I take 625 and I multiply it by 2/5 raised to the raised to the sixth power, I get this, gives me G sub 7 would equal a 64 over a 25. If I do, then I have to consider the negative scenario. And this one would have a seventh term that's negative, so negative 64 over 25. Oh, was I writing off the screen? I apologize. I forgot to look. Okay, anything else I want to say about that? Notice, I always default back to this equation. G sub n is equal to G sub 1 times R to the n minus 1. But I could have found the zero term. I just didn't. True story. Okay. For a geometric sequence, Okay, so let's see. We have b sub 8 is equal to b sub 5 times r to the third power. And so that would give me b sub 8 over b sub 5 is equal to, well, b sub 8 is 96 over 12. I think this equals 8. And this would be equal to r cubed. So if 8 is r cubed, then r is 2. And then b sub 15 would be equal to b sub 13 times r squared. So b sub 15 divided by b sub 13 is equal to r squared. We just said r was 2, so r squared is 4. So this ratio of the 15th term divided by the 13th term, we don't even have to find out what those terms are to know that that ratio will be equal to 4. Okay, an exponential function has a common ratio of -3, r equals -3, and includes the input-output pair. So this would be, I'm going to use my geometric sequence notation. And so this is like saying g sub 5 is equal to 324. Okay, so what do we know? We know that, you know what? Okay, I'm going to go out, I'm going to stretch myself and use this version of the equation, which is not what comes naturally to me. And that is g sub n is equal to g sub 5 times r to the n minus 5. They put that in parentheses. You don't have to put it in parentheses, but it does help you see that it's all the exponent. Okay, so let's plug in what we know. G sub 5 is this 324 times r is -3 to the n minus 5 power, which technically is an equation. So technically we're done. It's not very helpful to find the first term or things like that. But let me show you how we might clean this up. As we would say, this is g sub n is equal to 324 times a -3 to the nth power times a -3 to the -5 power. I'm going to do the -5 power first so that I can keep my variable just at the end. Notice how my exponents, I can give them both I can split that. And so I have 324 times -3 raised to the 5th power. I lied. I was like, that is not right. To the -5th power. Did you catch my mistake before I did? Good job. Okay, I'm looking at this. I'm not sure. Oh, okay, that's a -4/3. So what this is giving me is this becomes g to the n is equal to a -4/3. I don't need the parentheses, but I wrote them, times -3 to the n. And that's another version. This will show up in the multiple choice. If they don't have this, then clean it up and get to this in the multiple choice. All right, like, subscribe, comment, let me know how I can help you. And of course, go practice.